All right, part two of the threaded hole and various holes project. Basic sampling of holes, seven different holes. So we're doing the layouts for positioning with crosshairs and center punch, so it's semi-precise as far as positioning. As far as creating the holes, you can be very accurate with that, depending on what method you use. The first row of holes on the left are typical holes that we call clearance holes. And if you put a bolt through them, they have like a standard clearance that a shop standard was plus 15 thousandths or 1/64th. So in order to put a plate on top of something that's going to be bolted to something, you need to have a clearance hole. Can't be just like 0.25 hole would be 251 diameter. It's a little bit too close. It doesn't allow for any leeway. So we would go like 1/64th oversized, and I think on the Starrett chart it would be 17/64ths, I think, or 0.265. Then you have good example of this is locator holes. So the two holes in the middle row on the upper and the extreme lower end are almost exactly the same size, but they are very accurate. They have to be reamed, so you got to drill and then ream them. And the middle hole is a threaded hole that goes through. And the last hole on the right is a clearance hole, but it has an 82-degree countersink in it. All right, so there's instructions here, but I'm just going to go right to the print. Where's my print? Oops, sorry. I lost everything. Okay, I'm back again. So here's our print, right? Print is rules everything. So I'm looking over always look over the print to get a good understanding of what you're trying to do. All right, on the lower right it says 6061 aluminum plate, 2.0 by 0.375 thick, cut to 3.0 long with the saw. All right. And it shows 375 thick on the front view, and the top view, we got actually two top views, and the reason that was done that way because there's a lot of information and one view would make it too busy to see. So I'm going to look at the big numbers. So it's 3 inches long and 2 inches wide, and on the middle one it shows the three hole diameters on the left, 0.265, 328, and 390. Now these are all decimal, but we have to go to the wall chart to find out which drill or method would work. So these would be, you could drill these holes no problem, so I would center drill and drill those. The middle row I see 0.251 and I see 0.2495, so that tips me off right away that why do they want that specific number? It's not 0.250, so probably should put an additional note on the print, but I would ask my boss, like, what's up with that? They said, oh, those are going to be reamed, so we're going to ream those holes, and seeing I've done reaming before, I understand the process, but the process to do it is to pre-drill the hole slightly undersized, or 1/64th undersized. So that would be about 234 around there. So I'd find the proper drill for that, and so I'd center drill and drill those two holes with the same drill, and then I have to go find a reamer that's that size, 0.251 and 0.2495. So I would do that at the end. The middle hole is a 5/16-18 United National course, and same thing applies there. I have to pre-drill that hole with the proper drill. I look it up on the wall chart and it says letter F drill or 0.257. So the middle row, I'd have the upper and lower, I'm going to use the same 0.234 drill, and the middle one I have to drill it at 0.257. And then on my last operation I'll do reaming and tapping or threading. The middle hole, make that 328. That's you can use a drill for that. And the countersink, you can see the countersink on the front view, is 82 degrees. So I'm going to run that at half the RPM for the countersink and half the RPM for the reamers. So if I ran the drills at 1,000, then I'm going to use 500 for reaming and countersinking. But I got to have some way of controlling my depth on the countersink. So if I try to freehand it, I'm not sure how accurate I can be. So I have to set up some kind of drill stop on the head of the drill on the machine. So we keep on going down until you reach that diameter with, I would use a set of calipers and do a visual diameter check, because there really isn't anything you can grab onto, because it's not like measuring the outside of a shaft. Okay, here's another blueprint. This is a NIMS Manual Skills Level 1 print. So if I look at the print, I'm looking around, and I see a bunch of holes from the top view, and I see the side view. So the top view, I see two little dinky holes, and it says 2 times diameter 0.125 plus or minus 1,000. It's way up on the top there. It says plus or minus 1,000. Right away that tells me I cannot drill that, because I cannot hold that kind of tolerance with that. And there's also a symbol next to it that's pointing down that says 0.50. That's a thread depth. So, not thread depth, hole depth. So you got to get the hole to be that deep. So plus or minus 1 would require me to drill undersize, maybe like 0.118 or something like that, and I have to follow up with the reamer that's 0.1250 in order to create a nice precision hole and size and finish. So we're either making like clearance type holes for bolts to go through, which are okay with a drill. We can do, we're always countersinking all holes. You need to have a little chamfer on there. And that's typically a 90-degree chamfer or hand chamfering. Then you have threaded holes. That's the second most common hole. So they're either the thread is through or the thread is to a what we call a blind hole, like this picture here. If I look at the thread that says 0.250-20, that's the thread size. And if we look at the side view, I can tell it's not through. And in the specs, it says 0.500 deep, so that's how deep. So I would have to drill that hole out, pick the proper tap drill, and then follow up with the tap. So when I go to drill the hole, even though it says 0.5, I got to drill the hole deeper than that, because my tap won't reach the bottom because of that. First couple of threads are not full threads. So I would go probably maybe 0.150 before I break through the bottom, so it does not break through. And then when I'm tapping, I need to count turns, how many turns it goes, which would be like your pitch dimension. So quarter 20 is 1 divided by 20. You know, that's how many times it would take to travel an inch, is 20 turns. To travel a half an inch would be 10 turns. So if I can get the tap to go around 10 times, I should be pretty close. But I'm going to use a gauge to actually check how far I made it. And I could just follow up with the tap to finish it up after that. So that would be, I see 2 reamed holes and 1 tapped hole on that. And then there's another really big hole that says 0.750 plus or minus 5. Now that could be drilled because of the spec, and there's actually a chamfer on it also, so I'd have to figure out a way to do that, but it's that's not a big deal. But so you got a through hole, big, that could be just drilled out. You got a tapped hole that needs to be drilled to the proper size. So when you go to make these things, it's up to you to do the process. So the process to make a quarter 20 hole is to tap drill it and then tap it. And the same thing goes with reaming. In the other project, the the reamed hole had a purpose. One was going to be a slip fit for a pin, and the other was a press fit for a pin. So a sampling of holes. And I got some pictures here, hang on. Okay, to continue on. So this is a Starrett decimal equivalent chart like I handed out. This one's fairly easy to read. So you got all the decimals there on the left. And in the third column it says tap size, so it's not everywhere. So you look up the thread you're trying to create, like 5/16 which is right in the middle, and you look to the left and it says F.257. So that's the proper tap drill in order to follow up with the tap and create the threads. So that's how you figure out what tap drill size to use. Starrett's an American company, so this is mostly US on this print, but it actually has a small section for metric threads on the right. And down the lower right hand corner is for what we call pipe threads, or tapered threads for like plumbing threads. They're meant for sealing. Regular bolts can't seal liquids. See if I get any other diagrams here. Yeah, this is typical pipe thread sizes, 1/8 by 27. That's 27 threads per inch and quarter. So they'll say NPT, or National Pipe Thread. So like our air hoses have little nozzles on them, so they actually have pipe thread fittings on them, and they're 1/4 18 NPT. And there's another tap drill size chart right here. Let me blow it up a little bit. All right, so this is it's like a combination chart. It's got a lot of different sizes. So if I was trying to make a 1/2 inch, I wanted 1/2 inch 13 tapped holes. And it says cut taps. Cut taps are one to cut, and forming taps actually reform the metal. So there are actually two different size drills you need to use. So in this case, a 1/2 inch 13 thread requires a 27/64 drill, or the decimal equivalent is 0.4219. A forming tap requires a bigger hole, 468. So if you had drilled them to the cut tap and tried to use a forming tap, you would break the tap because the hole is still too small. And vice versa, is if you drilled it for the forming tap and tried to use the cutting tap, it would cut, but the thread would be too weak. It wouldn't have enough threads or minor diameter. A common drill in metric is 6 millimeter, 6 by 1.0. So in metric size, I happen to know that one off the top of my head. It's 0.236 an inch. And the second row is the size drill that we'd use, 5 millimeter, but we're in inch land, so we got to use an inch drill, and that would be 0.1969. So that would be the size drill you'd use for 6 millimeter. So we do both in this country, so you got to be aware of both. And so back to the reamer. Let me get the picture of the reamer again. Okay, here's the reamer. Okay, the upper left-hand corner is at a 45-degree corner. That's the only cutting edge on a reamer. So it needs to be, that's why the reamer needs to have some material to take out. If you drilled the hole 0.250 and it came out 249, and you're trying to make 0.2495, there's probably not enough material left to do it properly. If it came out like 247, you might have a shot at it. But the best idea would be like 10 to 20,000 smaller would be a good range to give the reamer enough material to just make that nice, beautiful honed finish. So hole making is a very important process. It's such a basic thing, but everyday use, I like to say that nuts and bolts and all that kind of stuff, very important thing. So Getting familiar with this chart in many different ways is going to be helpful, because fractions, we're using like a tape measure to measure stock, and that has no decimals on it. We got to convert because the blueprint is in decimal. So we're trying to cut material that's a little bit oversized, and you don't want to cut things undersized. If you can't read the tape measure properly, you're going to have material of not adequate size. Or if you went into the stock room to get material, you don't even know how to even measure to know which material to pull out, even though you might get the right material, not the right size. You really shouldn't go in a stock room without a tape measure, because you're in there to get something that's specific, and you need to know what size it is. So at least have a tape measure or a scale. Personally, I don't go in the stock room with a caliper. A caliper is too delicate of an instrument to be banging around in a stock room. You want to treat that with care. Caliper is probably the most common measuring device you're going to use, but then you go to micrometer, which is higher level. But you got tape measure, scale, semi-precise, caliper, digital or dial, and then micrometer. So, all right, enough of that. So this is like my big talk about hole making and stuff. So I know the 7-hole project is like a good sampling of holes, but we're actually going to do a lot more work with holes. So it's just a beginner of that journey. Okay, talk to you later.